Morning students, in the last class we discussed the oscillations lesson. Today also we are continuing the 10th unit, that is oscillations. So in that we are going to discuss the horizontal oscillations of a spring mass system. So for that what we are going to discuss means first how this the horizontal way, how it was connected, the difference of horizontal and vertical. So the two oscillations we are going to discuss in this. Before that, first we are going to discuss the horizontal oscillations. Okay, so for horizontal oscillation we are taking a system that is containing of a mass, that is a block of mass m, and that will be attached to the massless spring constant, that is a spring with the stiffness constant or the force constant or the spring constant K, the placed on the smooth horizontal surface. Smooth horizontal surface means it's a frictionless surface. So now we are taking that x0 has to be a equilibrium position or mean position of the mass. So when it is left undisturbed, suppose the mass is displaced through a if it is moved to a small displacement, that is a x, towards the right from its equilibrium position, then it is released and it will oscillate. So if you are moving and after that if you are released, means the spring will move, right? So that is the thing has happened here. So they are just moving that towards the right and after that they are leaving it, and now it going to oscillate. So that oscillate back and forth, its mean position at x0. So let F be the restoring force, that is the stretching of the spring, which is proportional to the amount of displacement of the block. And for a negative sign, so that is the for one dimensional motion, so they are given that force is directly proportional to the displacement. You know this. So F is equal to minus kx. This negative sign implies that restoring force is always acting on the opposite direction. So and then this equation is also called as an Hooke's law. You know what is the difference of Hooke's law? This Hooke's law you will getting in the 7th unit. So what is that Hooke's law? The restoring force is linear with the displacement, so the exponent of the force and the displacement are unity. So this is not always true, but if we apply a very large stretching force, amplitude of the acceleration becomes very large. So that means force is directly proportional to the displacement of the higher power of x. So oscillation of the system is not linear, and then it is called as a non-linear oscillation. You know what is a linear and non-linear? So this is a non-linear one. So we restrict ourselves only to the linear oscillation throughout our discussion. So which means the Hooke's law is valid. What is the meaning of it? Means the force and displacement have a linear relationship. So we know the Newton's second law. What is Newton's second law? Force is equal to mass into acceleration. So we can write the equation of the particle executing the simple harmonic motion, that is m d square x by dt square is equal to minus kx. So d square x by dt square is equal to minus k by m into x. We are getting this equation. We are comparing the both the equation. For that we are getting omega square. You know that what is omega? Omega square is equal to k by m, which means the angular frequency or the natural frequency of the oscillator is omega is equal to root of k by m. So the radian per second is the unit. So frequency of oscillation, what is a frequency? Time period, one inverse of time period. So what is time period? 2 pi by omega. So inverse of that is frequency. So that we are taken as omega by 2 pi. So that is 1 by 2 pi root of k by m hertz. And time period inverse of frequency. So reverse form, again we are taking that t is equal to 1 by f, that is 2 pi into root of m by k seconds. So in simple harmonic motion, the time period of the oscillation is independent of the amplitude. So time period is independent, not a dependent one. Okay, for this simple harmonic motion only. So it's only valid if the amplitude is very small. The solution of the differential equation for the simple harmonic motion is given as x of t is equal to a sin omega t plus phi, or x of t is equal to a cos omega t plus phi. So a, omega and phi, these are the constants. So general equation for differential equation is x of t is equal to a sin omega t plus phi plus b cos omega t plus phi, where a, b are constants. Okay, understood these things. This is the horizontal way of oscillations. Okay, now we are going for the vertical oscillations of the spring. Horizontal means it will be acted on the XY direction. If it is a vertical means it will be on the Y direction. So this you know the XY axis. So in the vertical way, what happened to the massless spring if it with the constant spring constant K? For that also we are taking for that horizontal we are taking a mass, but here we are taking a massless spring. So with the spring constant K, attach it to a ceiling. Let the length of the spring before loading was a mass M BL. So if the block of mass M is attached to the other end of the spring elongates of the length L. So if you know that if you put the load on the spring means definitely it will be elongated with the load, how much load you are making. Okay, so if F1 be the restoring force means due to the stretching of spring due to the mass M, the gravitational force acts. What happened to the gravitational force? It will be always acts on the downward, vertically downward. So we can draw the free body diagram for this system. So when this system under the equilibrium, F1 plus mg is equal to 0. That means the spring elongates by the small displacement of L. So it becomes F1 proportional to L. So F1 is equal to minus KL. So we are substituting the equation on that. So minus KL plus mg equal to 0. mg is equal to KL. M by K is equal to L by G. So suppose we are applying a very small external force on the mass means the mass further displacements downward by the displacement of Y. Then it will oscillate up and down. Now the restoring force due to the stretching of spring, total extension is nothing but Y plus L. That is F2 is proportional to Y plus L. So F2 is equal to minus K Y plus L. That is minus KY minus KL. So the mass moves up and down with the acceleration, that is d square Y by dt square. So we know that minus KY minus KL plus mg is equal to m into d square Y by dt square. So the net force acting on the mass is nothing but F is equal to F2 plus mg. F is minus KY minus KL plus mg. Gravitational force is always opposing force to the restoring force. So that we are getting that F is equal to minus KY minus KL plus K, that is equal to minus KL. Now we are applying the Newton's law. So Newton's law you know that. So we are applying that what MA is equal to F. So A is nothing but d square Y by dt square and F is minus KY. So that's why we are getting m d square Y by dt square equal to minus KY. So d square Y by dt square is nothing but minus K by m Y. So this above equation is a form of a simple harmonic differential equation. So from this we are getting a time period. So time period is nothing but you know that t is equal to 2 pi. I already get this in the horizontal oscillation. So root of m by k seconds. So time period can be rewritten as for this 2 pi root of L by G. So acceleration due to gravity can be computed from the formula, that is G is equal to 4 pi square L by T square meter per second square. Understood these two oscillation, that is a vertical and the horizontal oscillations. Next we are going to discuss about the combination of the springs. We will see the springs in many places. So the combination of spring as a shock absorber in the motorcycles. Spring constant or the force constant also known as a stiffness constants. So it's a measure of a stiffness of the spring. So large the volume of the spring constant, stiffer is the spring. So this implies that we need to apply more force to compress or elongate the spring. Similarly, the smaller the value of the spring constant, the spring can be stretched, that means elongated or compressed with the lesser force. Springs can be connected in two ways. Either the springs can be connected end to end, also known as a series connection. So you know in the wire connection we are telling that no series, same like for the spring, and we connected with the parallel, you know how it was connected. In the following subsections we compute this, that is springs are connected in series and parallel. So springs connected in the series, when two or more springs are connected in series, we can replace all the springs in series with an equivalent spring, that is a effective spring. If you know this, in the resistance, effective resistance we are getting from the series resistors in series, no, same like the springs also effective springs also there. So now whose Yet net effect is the same if all the springs are connected in series. Given the value of the individual spring constant, that is K1, K2, K3, known quantity, we can establish a mathematical relationship, that is an effective spring constant Ks. So for simplicity, we let us now consider two springs whose spring constant are K1 and K2. It is attached to the mass of M. Okay, so now we are going to write the number of series. So the force is applied towards the right, since the spring constant for different springs are different and the connection points between them is not rigidly fixed, so the strings can stretch in different lengths. So what happened, if you are giving the force, the different connections will have the different stretching. So let x1 x2 be the elongation of the springs from its equilibrium position. So due to the applied force, the net displacement is x is equal to x1 plus x2. So like this. So the diagram is clearly given for this. So it was stretched. Okay. So f is equal to minus kx into x1 plus x2. So x1 plus x2 is equal to f by ks. So springs in series connection means minus k x1 equal to minus k x2, that is equal to f. So x1 is nothing but minus f by k1, x2 is equal to minus f by k2. So what is the effective spring constant? Minus f by ks. Okay, same, minus of minus equal to minus of f. So 1 by ks is equal to 1 by k1 plus 1 by k2, that is ks is equal to k1 k2 by k1 plus k2 Newton per meter. So n springs are connected in series. The effective spring constant is series is 1 by ks is equal to, you know how to write the summation, same thing. I will take the number of values, the integers, so that is 1 by ki. So all the spring constants are identical. So k1 equal to k2 up to kn, then 1 by ks is equal to n by k, that is ks is equal to k by n. So the effective spring constant reduces by the factor of n. So hence the springs is in series, the effective spring constant is lesser than the individual springs. Okay, so kx1 equal to kx2, the ratio of the compressed distance, elongated distance, x1 x2, we will get x2 by x1, so k1 by k2. So elastic potential energy u1 is equal to of k1 x1 square, u2 is equal to of k2 x2 square. So we are substituting that, we will get k2 by k1. Okay, understood? This is the springs connected in series. Now we are going to discuss the springs connected in parallel. When two or more springs are connected in parallel, we can replace all these springs with an equivalent spring. That means the net effect is same for all the springs are connected in parallel connection. What the values of an individual springs is k1, k2, k3. So we can establish a mathematical relation with the effective spring constant kp. So for simply let us taking the two springs of spring constant, that is k1, k2. So that will be connected to the mass m. So what is the general net effect for that, we will find out. So see here, this is a diagram of the parallel connection. With the load, the two springs are connected. For this also, now we are going to apply the force towards right, and both the springs elongate or compress by the same amount of displacement. So what happened in the series, the elongation will be different in different springs, but here the elongation or the compression will be same in the both the springs. So here f is equal to minus kpx. Kp is nothing but effective spring constant. First spring elongated the displacement x on the force f1. Second spring also x, because the displacement is same, on the force f2. So we are getting the equation as f is equal to minus k1x minus k2x, that is kp is equal to k1 plus k2. So what the summation we are getting, kp is equal to summation of I is equal to 1 to n ki. Okay, so this is the thing we are getting. If all the spring constants are identical, means k1 equal to k2 up to kn, so kp is equal to nk. This implies as the effective spring constant, that is for the number of n. Springs in parallel connection means the effective spring constant is greater than the individual spring constant. We know that whatever the things in the series is different from the parallel. Understood?